Thank you very much, and thank you everyone for coming to hear my presentation this afternoon. As my title suggests, I'm going to be talking about some of the sustainability challenges facing shale gas extraction. And the goal of today's talk is to provide some fundamental understanding of what is hydraulic fracturing, how has the combination of hydraulic fracturing and horizontal drilling allowed us to begin to develop shale gas resources in the U.S. and abroad, and what are some of the key challenges that we face both as researchers, regulators, and industrial stakeholders to do this in a sustainable manner. And so to outline my presentation, as I said, I'm going to define hydraulic fracturing. I'm going to show you a video and talk a little bit about what it is. And then I'm going to actually spend the rest of my presentation discussing shale gas extraction in a much more broad sense. And we'll see, I'll show you sort of the shale gas life cycle, and you'll understand what I'm talking about here in just a minute. But one of the key starters for this presentation is discussing why you're all here to hear about this topic. Why are we talking about hydraulic fracturing, shale gas development? And I'm going to make an argument that it has a lot to do with the scale, the rate of the application, and the fact that we still have many open research questions related to this new energy technology. Briefly, we'll talk about how shale gas is changing the U.S. energy outlook, and we'll look at how natural gas production has been fundamentally shifted, and that's driving growth in chemical industry, for example, and other natural gas applications. For example, we could remove coal-fired power plants with natural gas combined cycle, and what does that mean from a climate perspective? And then the remainder of my talk, this is probably where we'll spend most of our time, is discussing the shale gas life cycle. But before we jump into this, I wanted to take us all back into the subsurface and discuss the origin of oil and natural gas. And I like this figure. I borrowed it from the New York Times because, actually, are we able to dim the lights a little? As I'm pointing at my figure, I realize we can't see it. So what we see here is that you have actually a river dumping a sediment load into an ocean. And what comes with that is a lot of organic material and nutrients, which leads to growth of microscopic organisms, for example, here in the ocean. And over time, the sediment and these organisms settle into the ground and actually form shale. So what we're seeing here, kind of in sped up time, is the formation of organic rich shale layers. And then if we look down, we can see that they have black shale showing you migration, oil, natural gas, and a traditional trap. So this would be a conventional reservoir. So if we want to think about oil and gas drilling, pre-shale gas discussion, this was, you had oil and gas company would go out and they would look for these structural traps, and they would look for organic rich shale layer below that formation, and then they would drill a hole and hope that they could hit some oil, right? And that would be the conventional reservoir, where you have a reservoir that holds oil and natural gas and has both good porosity and good permeability. It's sort of like sticking a straw into a sponge, right? You can suck up the water in the sponge. And the natural gas and oil that was trapped in these formations was naturally seeping out of the shale reservoirs, right? And we've known for a long time that these black shales contain a lot of oil and natural gas that hasn't escaped, right? But we didn't have a good way of going after it. We didn't have an economically efficient production strategy. So even though everyone knew that there was oil and gas to be had in these formations, they sort of left them alone and just looked for the rocks above them that had accumulated the oil and natural gas through natural seepage. And so when we discuss shale gas, we're talking about shale as both the source and the reservoir, right? So when you have an organic rich shale and it's exposed to the right temperature and pressure conditions, it breaks down, the organics break down into kerogen, which is a precursor to oil, and at the right temperature windows, it'll either go from oil, natural gas, or all the way to CO2. Right? This is determined as the oil window or the natural gas window, and it's a temperature pressure regime. So if you have an organic rich shale, you're also going to run into very low permeability, right? So you have lots of clays, these fine sediments. So thinking back to that river dumping into the ocean, a good example of that would be the Mississippi River dumping into the Gulf of Mexico, right? If anybody's ever seen the Mississippi River, it looks like chocolate milk, right? All of that is turbidity. So this is very fine particles, usually on the order of less than 4 microns. And these particles settle down and form layers, which you can see here. This is a pen for scale. Layers in this direction. So you do have bedding in these shale formations. However, the natural gas that is trapped in these shales tends to be in these nanopores or submicron pores, and it's adsorbed to the clay minerals and organic material within the rock. And so what this means is it's basically stuck on the surface. And in order for us to get access to it, we need to do two things. We need to overcome the low permeabilities of these formations. So remember how I compared a conventional reservoir to a sponge where you could stick it in water and the water is held in the sponge, but you could put a straw in and pull that up, right? Another way to think about porosity and permeability is if you had a jar of marbles, that jar is full, but you then fill it with water. The volume of the jar hasn't changed, and so the water is sitting in between the pore spaces, and you can suck it out or you could pump it out, and that would be a conventional reservoir. These shales are unconventional in that it's more like taking a textbook and putting it in a bathtub, right? So the water gets in there, but you can't necessarily put a straw in the book and pull it out, but you know that the water's been soaked up into the book, right? That would be kind of an analogy that you might be able to think about. So the first thing we have to do is overcome those low permeabilities, and the second thing is that we have to create pathways and increase surface area for the natural gas to come off the rock and flow to the well. And so that is where hydraulic fracturing comes into the picture, right? So shales are almost always the source of oil and natural gas no matter where we find it, and now we're going after them through new ways. So this is a great video. We're being videoed by MConnects today, and so I'm really getting a lot of usage out of this. This was from a short video that I did a couple years ago where they put together a schematic showing what hydraulic fracturing looks like in the subsurface. So in many ways, it's just like any other conventional well. But we're drilling down from the surface. You're going to case the well and cement it in below the lowest freshwater aquifer. But the difference often with shale gas wells is we're going to deviate the well in the horizontal direction. And these are steel pipes, but you can bend the pipe at about 10 degrees per 100 feet. And so after a while, you're actually drilling straight at the surface and horizontally in the subsurface. This is then followed up with a perforation gun here, which actually initiates fractures. It basically initiates cracks in the casing of the well and into the rock. They follow this up with water, sand, and a mixture of chemical additives at very high pressures and literally crack the rock, right? Hydraulic fracturing is fracturing with water. The sand is really important in this case because what it does is it serves to hold open those fractures. So if you think about the building being held up by walls, these sand particles serve as pillars that actually, when the water is released and the shale closes back on itself, serve to keep those pathways open. And then so the gas or oil is able to find a pathway back to the well. And so what's also being shown here is the return of a lot of the water that's injected. So we'll talk a little bit about the volumes of water that are consumed in an average high volume shale gas well. But approximately 10 to 30% of the water that's injected does return to the surface. And that is termed flowback, right? So this is prior to production. So they collect some of the water they injected, and then you see here the production gas that's coming up. So the point of this video and the next thing we're going to talk about is that these are actually conventional techniques. So horizontal drilling and hydraulic fracturing were not new techniques, but they're being combined at larger scales and in new ways to go after an unconventional reservoir in the shale gas in this instance. So a brief history of fracking. The first well that was fracked, I believe, was in 1947. And the whole idea here is that we're cracking a rock to enhance near well permeability, right? So this was a well where they actually used gelled gasoline, so napalm. So I think we've come a long way with using water from napalm, so that's at least a step in the right direction. However, many alternatives exist to hydraulic fracturing. So you can use nitrogen foams, liquid propane gas, CO2, etc. So any sort of working fluid that you're able to pump at high pressures and generate fractures within the formation can work. So we're talking about fracturing with water relative to napalm. Perhaps maybe that's not such a bad thing. So why all the concern and attention? And this is where I'm going to talk about why I believe it has to do with the rapid deployment and the scale of this application. So what I'm showing you here is a map from the EIA. This is the Barnett Shale. So this is one of the first shale gas reservoirs that was developed with the combination of horizontal drilling and hydraulic fracturing. And starting in 1982, they were drilling wells in this shale formation, and you're going to see them show up as black dots here. This is near the Dallas-Fort Worth area. Down here it shows where we are. This is total shale gas production from the Barnett. It's pretty flat right now. So if you look at the shale gas production down here, you'll see that when the red dots start to show up, these are horizontal wells. So all the wells that they were drilling here were fracked, but when they started putting in a horizontal well, you start to see an uptick in production. Then by about year 2005, you see more red dots coming on the scene, much more gas being produced in the Barnett Shale, and pretty soon, all you see is red dots. These are these high-volume, hydraulically fractured wells. So horizontal drilling coupled with hydraulic fracturing. And this is a great example of why people are talking about it. Because let's imagine you used to live right here. They were drilling in your area, but you didn't necessarily see it. And then in a period of 5 years, it went from, well, maybe they're developing oil or gas over there, to you see trucks on the road every day. And you see drilling in every direction you look. And so this kind of rapid expansion is what draws the attention of everyone who lives in this community, right? And it also leads to increased demand on water resources, et cetera, things that we'll discuss in today's presentation. What does it look like across the United States? This is a map that maybe some of you have seen. I think every time I go to any presentation where someone's talking about shale gas, this map pops up. And what it is showing you is the shale plays across the United States. So we were just looking at the Barnett, which is here. And the next thing I'm going to show you is an image of the United States at night. So keep in mind where some of these resource plays are: Bakken, Eagle Ford, Barnett. So this is what the US looks like at night. This is an image, a satellite image from NASA. And you see up here in North Dakota, big city of Williston, Minnow, Bismarck. And you wonder what this is, right? What large city is, it's on the same order of magnitude when you look at sort of the light pollution is LA, Chicago, Detroit. This is the Bakken Shale, right? So this is actually not shale gas. So I'm stepping out of my title here a little bit. But this is now makes the US one of the largest oil producers now in the world. And that is shale oil. This is, instead of natural gas, you're getting oil from these shales. Also, what you see down here, the Eagle Ford Shale. So the light that you see is due to a couple things. In the case of the Bakken, it's due to 24-hour-a-day drilling and flaring of associated natural gas. And that is when you have oil production and some amount of natural gas, but you don't either have the infrastructure in place or you don't have enough natural gas to make it economical, that they actually flare it, where they burn it off. So if you've ever seen those images with the tall tower with the flame at the top, that's flaring of the natural gas, which is better than just releasing it to the atmosphere. Right? And over here, this is mostly the same thing. And we just, basically, I like to use this slide to show you that scale matters, right? We gave that example, the Barnett Shale. This is, the case of it's happening across large geographic tracts and at a very rapid pace. And how is this activity altering the U.S. energy landscape? I'm just going to show one figure to demonstrate this. And this is the newest EIA projections for natural gas production. This is domestic natural gas production. And what we see here is that this is where we are now. If we come back to 2005, that's where shale gas was. So this growth here is that, the last, 8 or 10 years. And shale gas is going to go from 35% of our total natural gas production to upwards of 53%. And what I'm not showing in this figure is also from the EIA report, is that the total natural gas proven reserves are expected to increase. So it's not that we're using up our natural gas. We're just drilling more wells, and we're finding more gas, and we're producing more gas. And I would argue that all of the growth you see here is due to unconventional reservoir development. So we talked about shale gas as being an unconventional reservoir. Tight gas is natural gas that's found in other low permeability formations. So these could be tight carbonate reservoirs or tight sandstone reservoirs, which are often also produced through a combination of hydraulic fracturing or horizontal drilling and hydraulic fracturing. So this is a game changer from an energy production standpoint. So that's our introduction to hydraulic fracturing, talking a little bit about shale gas, where we get it and why it's there. This is the rest of my talk. I'm going to discuss what I describe as the life cycle of a shale gas well, right? Everything from pre-production, which is site development, to production or well completion technologies, to post-production, which is how do we handle wastewater streams, What happens with the natural gas? Do we use it for power generation, heating, etc.? And the areas that we're going to lay out here, we have sort of graphical depictions, but pre-production, Wellpad construction. So this is where you've now purchased the rights to produce in a given tract of land. So you go out there and you get permits to make your well pad, you clear it, and there's a whole process which is making you ready to actually bring the drilling rig out and drill your well. Water acquisition and transport. That's a big issue that I think a lot of people are talking about with regard to these wells because they're often described as being high volume hydraulic fracturing wells. And so I'll give you an order of magnitude estimate as to what that means when we say a lot of water is consumed. And then also issues with chemical transport and equipment transport. Well completion. So this is within the production phase. Hydraulic fracturing, the actual step of fracturing the well. So what we saw in that video is described often as well completion. So you've drilled your well, you've cased your well, and you come in and you complete it. And one of the completion steps is perforating it and fracturing the well. Right? And so that happens here. After that takes place, and you put in your production infrastructure, you have flowback collection, and then you can produce your natural gas well. And then finally, when you get to post-production, so the well has been completed, you're done fracking the well, you come in here and we worry about some of these issues. So I have question mark here because one of the biggest contentious issues related to shale gas development is whether or not it is good or bad for the climate. And it hinges on how much methane is being lost during the process of completing the well to bringing it to your home. And then I'm also going to spend a lot of time talking about wastewater management because I think that is also one of these key issues that is often brought up from a sustainable development standpoint, and a public concern is related to how do we handle these enormous volumes of produced and flowback water from the rapid deployment of these shale gas wells. And then tied to the methane emissions and climate is what do we do with our natural gas? Do we use it for heating? Is it used as an upstream for ethylene crackers or something at a chemical industry, or do we use it for electric power generation? And I've chosen to isolate 4 of these topics. And what I want to point out here is that oftentimes the media, or even in just day-to-day conversations, we talk about shale gas development as fracking. And fracking is used as like an umbrella term to cover everything you see here, right? But the actual process of hydraulic fracturing is right in the middle, and it's a very short period. And this is, I think, where poor communication happens. If you have someone from industry come in here and they say, well, fracking isn't related to wastewater management. Fracking isn't related to methane emissions, right? And they're going to make this argument. And that actually is a not very constructive way to talk about sustainability or sustainable development of shale gas. But I titled my presentation Shale Gas Extraction because I'm talking about the entire process here, right? So we're done talking about hydraulic fracturing as the stimulation technology, and now we're going to move to talking about some of the bigger challenges related to surface development, water acquisition, methane emissions, and wastewater management. So Wellpad construction, as I said, prior to completing a well, you have to come out and you clear the surface. This is a great image, just for scale. These are semi-trucks, and those are shipping containers, right? So I don't think we see people on there, but that gives you an idea of how big we're talking about. And these high-volume horizontal well pads tend to be cleared at the scale of 5 to 10 acres. Compare that to a more conventional well, or a vertical well that's targeting a conventional reservoir, and you might have maybe a 1-acre well pad, right? So these are larger in space as well. And so what does that mean? It means you have more trucks who move the water there, who come and mix it. These are all mixing trucks, and this is where they're holding the water. So basically you have sand and water coming together, mixing here, and being pumped down the well to complete it. That's what we're looking at. But you also have larger surface areas, so you can have increased surface runoff, which can lead to increases in stream turbidity. And so those are some surface, ecological, environmental challenges related to these larger well pads. On the flip side, you could make the argument that the cumulative surface impact is smaller. So from one well pad, shown here, you can drill 8 wells versus the equivalent of that many vertical wells to tap the same volume of the subsurface. Now, this is true, but I don't think that it necessarily holds in this case because as I said before, we always knew that these shale formations may have held natural gas and oil, right? But we didn't have an economical way to go after them, which means this doesn't make economic sense. So they're not going to do it. So we're basically setting up a straw man in some cases to compare one versus the other. But it is important to show how one pad can access an enormous volume of the subsurface. This is an image from Statoil where they show here's 4 well pads coming down, and they have 6 horizontal wells. So as I said, you can drill down and then deviate in any direction. The drilling technology is amazing. If you think about back to the the Gulf of Mexico oil spill, right? How did they solve that? They brought a ship over 5 miles of water and drilled down and hit a 4-inch pipe, right? So consider that for a second. Or maybe it was 1 mile deep. Anyways, that's how well they know where the drill bit is. So they can do this with fairly good accuracy. But as I said before, this isn't necessarily the same as that, a lot of vertical wells. This is showing you a horizontal well. If we think about the cylinder of rock, or sort of the volume that's being accessed here, this is a good depiction, whereas one well is there. I think when I give similar talks, I have a chalkboard usually, and so that's when I break out the chalk and I show you. I think it's a great example of showing you how one well is able to efficiently capture an enormous volume of rock, right? But what you have here is multiple fracturing stages. And so this is actually one of the keys for why they use more water to complete these wells on a per well basis. So that's a good segue into a discussion of upstream water concerns. And I say upstream, which is now on our shale gas life cycle image, this is pre-fracking. So what happens, where do we get the water, what chemicals are added to it, etc. So as we said, these wells can consume millions of gallons of water, right? High volume hydraulic fracturing wells, which, depending on where you are, can have either increased stresses on local water resources or potentially negatively impact shallow groundwater or groundwater-fed streams. And so that's a concern that we have to think about from a sustainability standpoint. In addition, chemical additives. This is just a list of some of the common chemicals which are used to complete wells in the state of Michigan. And they range from, guar gum, which is often cited. This is used to actually viscosify, so it makes a gel, right, which allows them to pump it down. This is a common food additive, right? However, but you also have things like butoxyethanol, methanol, isopropyl ethylene glycol, things that you necessarily don't want in your water. But the bigger problem, I think, related to chemical additives is that there's not full chemical disclosure, right? And so I stated earlier, I thought that one of the challenges facing development of these shale gas reservoirs is poor communication between stakeholders and industry. And this is a key example, right? So you often hear everybody talk about chemical disclosure and not being, how do I know what to look for in my water if I don't know what was used in these wells? I think most industry operators that I speak with are not concerned about this ending up in your drinking water, right? So the question is why aren't we getting full disclosure? And that, I think, lies in the proprietary, standing. So what part of the recipe is proprietary? And so that's something that is getting a lot of regulatory attention, and I think is a conversation that needs to be fully developed as we move forward with developing these resources, just so that there is trust across the board. Water use. So these are a range of wells that have been drilled in Michigan. There's not a lot of high volume hydraulic fracturing activity in Michigan, but what is here tends to be at a much larger scale than the average shale gas well that's being produced across the US. So we see here 2 wells that were completed using over 12 and 21 million gallons of water respectively. So these wells were approximately 9,000 feet deep and had horizontal legs on the order of 1 mile. And so maybe 20 different frac stages. So you use about, these are average numbers, but maybe 500,000 gallons of water per frac stage. But how much water you use depends on how deep you are, how far out you are, right? It's basically a column of water that you need to maintain a certain high pressure. And if you're deeper, then you have to have higher pressures to overcome the stress of the rock, right? So these are all things that weigh into how much water is consumed. The average water consumption across the major shale plays, so this would be Marcellus, Barnett, Eagle Ford, Bakken, is on the order of just shy of 4 million gallons of water, right? So these are extreme examples, but that's still, we're talking millions of gallons of water per well completion. And again, what's that?
Where would that water come from?
So that was earlier. So the question was where does the water come from? And so it depends where you are. In areas where water rights are a challenge, for example, sort of west of the Mississippi, oftentimes they're purchasing water either from municipalities or private landowners. East of the Mississippi where water, so for example, Michigan, you just get a permit to drill a well and you can pump, right? So as long as, it's almost always groundwater, sometimes surface water, but groundwater by and large, yes. But one of the points that I also like to make is water use intensity. Leland and I were discussing this prior to the presentation. This is a table from a recent review article by Jackson et al. And what they show you here is water use intensity for various energy sources. So we have natural gas, and then whether it's used in combined cycle or once through electric power generation, compared with pulverized coal, oil shale, nuclear power, etc., corn ethanol. And I'm just highlighting 4 here to compare. And we look at the water used per million BTUs generated. So this is sort of water per energy output. We see that hydraulic fracturing stacks up pretty well, actually, and very well compared to irrigated corn ethanol. But one of the points, so 2 things you can take away from this kind of figure. One, if we're just looking to maximize our energy output per water use, it's not so bad. It's a lot of water used at a short period of time, and then there's no more water consumption in the extraction process. There is water for cooling towers downstream, but it's fairly efficient even compared to pulverized coal. But a key differentiation, though, is that it's important how we define water consumption. So if we think about how much water goes into irrigating corn crops, right, that water either leaves as runoff, exists in the biomass, or we lose it to evapotranspiration, right? So it's still somewhere within the hydrologic cycle. Water that's consumed to complete these wells is effectively removed from the hydrologic cycle. And we'll talk about that in the next, so I think, next I'm talking about air quality. So I'll finish on wastewater management, and we'll talk a little bit more about what that means. But remember, as I said, you inject, say, 4 million gallons in the subsurface, you get 10 to 30% back, right? And then it's what do you do with that water? So you've already lost, say, 70% of your water. And by loss, I mean it's been imbibed by the shale, all right? So it's effectively trapped in the subsurface. But the water that comes back up is either reused to frack another well or probably, most likely, disposed of in another deep injection well. So we take it and put it back underground somewhere else. So when we think about water use from a sustainability standpoint, it is important to consider how efficient shale gas can be for water use, but it's also important for us to just define what is water consumption, right? Gray water, so it's thinking about sustainability and water footprints. Air quality and climate impacts. This is not an area that I research in my group here at Michigan, but this is an area that I think has probably received the most attention related to shale gas extraction. And some of the keys are from a local standpoint, right? If you live around the well or you're working above the well, you're worried potentially about volatile organic compounds. BTEX is a good example. This is benzene, toluene, ethylene, xylene, truck exhaust on site, sort of local air quality concerns. From a global standpoint, we're worried about methane leakage. And this has to do with whether or not shale gas development is good or bad for the climate. And it hinges, as I said earlier, on what is the methane leakage rate. So if you replace, as an example here, this is just a subset of titles from the academic literature which agree, disagree. Some say shale gas is great, shale gas is bad, and it's all about what leakage rate they're assuming and whether or not the natural gas produced from shales is replacing coal-fired power plants. So if you replace a coal-fired power plant with a natural gas combined cycle on a energy per CO2, you're going to get lower carbon emissions, lower CO2 emissions from burning natural gas. And so that is the plus side of the climate discussion. But if you have a little bit of methane that leaks, on the order of a few percent of total production, you've lost all benefits that you just gained. And that has to do with the fact that methane has a higher global warming potential than CO2. Depending on whether you integrate over 100 or 20 years, it's somewhere between 28 and 75 times more or a higher global warming potential than CO2, right? So it's quickly can shift our discussion of whether or not shale gas is benefiting the climate. And as I said, the biggest challenge with determining this is estimating leakage rates and confirming the source of methane. So I've mentioned communication a couple times in this presentation already. I would argue that there is equally poor communication on the anti-shale gas side of the discussion, right? When you see videos of everybody lighting their water on fire, that is, everybody goes, oh my gosh, what is going on, right? But what you miss there is the fact that you do have natural seepage, and you have, I think this is 7 different potential pathways. This was from a recent paper by Dara et al. and PNAS, where they looked at noble gas isotopic signatures and methane, carbon and hydrogen isotopic signatures to try to determine whether or not methane that was found in groundwater was from the target formation, existing gas pockets, natural seepage, or biogenic methane. So in Michigan, we've been producing shale gas from the Antrim Shale since the 80s. We were one of the largest shale gas producers. And most of that gas is biogenic in origin and has a distinct isotopic signature, which is different from thermogenic, which would be the gas that was created under temperature and pressure. And so what they found is, looking at wells, I think in Pennsylvania and Texas, the instances where they had elevated methane in the water, they weren't able to tie it to leakage from fracking out of the formation. And almost always, it was tied back to casing failures or improper well casing or cementing of the well. And that is not unique to hydraulic fracturing. That's just, if you drill 1,000 wells, maybe one of them doesn't have a good casing, right? Or you didn't get good cement adhesion on the side. And so that's just an opportunity for us to improve best practices across the industry as a whole, right? But when we see someone with methane in their water and they're complaining about contamination, we need to be able to tell what it was like beforehand, right? So that baseline sampling is key. And in many cases in Pennsylvania, earlier on, they went in and started drilling before they went and sampled everybody's water. And so the baseline is gone. And so you don't know what it was like before. But there are definitely cases where they're drilling water wells and hit pockets of natural gas. And so trying to break that out is quite important if we want to really nail down what the leakage rates of methane are related to this practice. And as an aside, I think about this from an infrastructure standpoint. A lot of recent funding announcements have been targeting water infrastructure in aging urban systems. And Jackson's group has also been looking at aging natural gas transportation systems. And they've been running around DC, Boston, and basically sampling methane leakage across the city. And here's an example for DC. So here's the White House. 40 ppm, 28 ppm. The average atmospheric concentration of methane is 1.8. So what you have right here is a city with a natural gas distribution network and aging infrastructure, which is going to, on estimates here, so here is DC, and this is talking to the utilities in DC, is how long would it take to go and replace all your cast iron piping across the city, and they're estimating, I think, on the order of 80 years, right? So if we're worried about methane leakage, we need to think about it from a cradle-to-grave perspective. So if we're going to shift to use more natural gas, it's not just what happens at the well site. It's what happens when you take the gas from the well to the transportation, to the power plant, or to someone's house for heating purposes. So I'm just, the point here, sustainability talk, is that the challenge is bigger, and it's not just one aspect that we should focus on. Finally, in the last 10 minutes of my presentation, we're going to get back to water, right? So we talked about that water that comes back up to the surface. I called it flowback water. So what's in it? Here's an example of the Antrim Shale. This is looking at TOC, stands for total organic carbon. And what you notice is that the Lachine and the Norwood, these are the producing zones of the Antrim, right? And they have higher organic carbon, which means that they're going to be more likely to have natural gas, right? But you also see an increase gamma log, which is basically a measurement of the radioactivity of the rock. And oil and gas companies have been using this forever to target organic-rich shale layers, right? They find these spikes in the gamma ray log here, and they say, okay, that probably has a higher TOC, and then they look above that, right? And what happens is in these shale formations is you have excess organic material, which over time maintains reducing conditions. And naturally, as water flows through, you accumulate, for example, uranium in its reduced form. And so shales accumulate naturally occurring radioactive material, right? In addition, deep reservoirs often have high total dissolved solids. So this is the salinity, right? So we see here Michigan, the Appalachian Basin, Illinois Basin. You know, in Michigan, once you get down below 800 meters or so, you're on the order of 300 grams per liter salt. So does anybody know how salty the ocean is? About 35 grams per liter. So we're talking an order of magnitude more salt in these reservoirs, right? So you have water that's coming back to the surface, very salty, potentially containing elevated concentrations of naturally occurring radioactive material. One example would be radium. And in addition to the chemical additives that you may know or may not know what are there. So from a treatment standpoint, if I don't know what's in the water, it's really hard for me to design a treatment strategy to target those contaminants, right? And it comes back salty and containing constituents of concern. For example, you might also get arsenic and other water quality contaminants. So the key here is now that we must ensure proper disposal or handling of these fluids at the surface. But it's not that simple. And so this is an example of shale gas production in the Marcellus Shale. It's a figure from Lutz et al. Here, which shows you where the brine disposal wells are and industrial treatment facilities, and then the little red dots are all the shale gas wells that have been drilled in Pennsylvania. So between 2004 and 2014, roughly 12,000 wells have been drilled in the Marcellus Shale. There's about 3,500 producing wells, and this has led to a tenfold increase in wastewater that has to then be managed in Pennsylvania. So they have over, an annual wastewater pool that they have to handle on the order of 1.4 billion gallons per year, right? And they have 7 brine disposal wells. And so, as I said before, most water that's collected from these wells is reinjected into the subsurface. Well, you have a state where there's an enormous amount of shale gas activity that's rapidly kicked up, and they don't really have a good place to handle it. So what happens? We ship it to Ohio. Huh? So, I say that in jest, but in reality, they actually did send a lot of their wastewater to Ohio. And that led to instances of induced seismicity, right? And so this is a topic that people talk about, and they say fracking causes earthquakes. And by and large, felt earthquakes, so I think larger than magnitude 3, are all related to wastewater disposal. So not the actual process of fracturing. So this is an example where the media isn't getting it right, and then that's skewing the whole conversation. So I have a presentation and everybody says, well, I heard this. So this is my example of trying to show you what the real issue is. And the real issue is that we have an enormous amount of water that we have to handle, and we don't have good ways to treat it. And so, over 95% of this wastewater, and so I said flowback water, but after you have flowback and production, you do still collect water through the lifetime of the well. And this is true for all oil and gas production, right? So it's not unique to shale gas. But when you have, shale gas growth, at a rate of you saw that sort of 0 to 60 kind of increase in shale gas production, you have a concomitant wastewater challenge that comes with that. And so, a good example is, this is from a paper in Science by Karen et al., where they looked at earthquakes in Oklahoma. So here you have instances of earthquakes, and the squares, which you can see, are wastewater injection wells. And then this is a model where they looked at pressure perturbation. And so they have a wastewater injection well here. These are now wastewater injection. And over time, in 3 years' time, the increase in the color gradient shows you, this is megapascals, it shows you the increase in pore pressure. And so what happens is you're injecting large volumes of fluid in the subsurface, and that creates higher pore pressures, and those pore pressures reduce stress on faults. And so you have existing faults that were kind of stuck, and now it's a little bit easier for them to slide. A good example that I think I was reading in this paper or somewhere else, which was if you have a heavy box on the floor, if you remove some stuff from the box, it's easier to slide along the floor, right? So think about this. And So this is the case. Is what's happening is they saw an uptick in the number of earthquakes related to high volumes of wastewater disposal. So Mark Zoback published a paper in 2012, which with 5 rules that he outlined here for safeguards and best practices. I also like to describe this as common sense, right? Avoid injection into active faults. Okay, makes sense. Limit injection rates to minimize increase in pore pressure. So do it slowly. Install seismic monitoring arrays. Okay, make sure you know what happens after you start injecting wells, or into these wells. Have established protocols in place in case some seismic event arises. Right? And finally, reduce injection rates or abandon the well if you trigger seismic events. Right? I think this is a great example of how some really straightforward approaches can help us avoid some of the challenges related to disposing of these large volumes of fluid. Right? But in the case of Pennsylvania, right, we had 1.4 billion gallons of wastewater generated a year, 7 brine disposal wells. So they did send some of it to Ohio, and they did send some of it to brine disposal wells in Pennsylvania. However, it's very expensive, and so they found alternative means of disposal and treatment. And prior to 2011, it was perfectly legal and permitted to send 1% of the intake for a wastewater treatment facility could be from oil and gas production, right? And this kind of goes with the idea that dilution is often the solution, right? That is generally true. However, not quite here in this case, because you have wastewater treatment facilities that are designed to take out biosolids and not treat high salinity fluids. So if we look here at this summary here, this is bromide, average of about 511 milligrams per liter. That's a lot of bromide. And then you also have elevated radium, right? So I mentioned radium as a concern, right? So this is shown in picocuries per liter. So what happened? They were sending these fluids to wastewater treatment facilities, which then put it through their treatment process. And then when the water is treated, it comes back out and goes into the Monongahela River. And somewhere downstream, there's a drinking water intake facility, okay? And when you have a drinking water intake facility that's bringing in water that has elevated bromide concentrations, you get the formation of trihalomethanes, which is brominated disinfection byproducts. So this is definitely something we don't want in our drinking water. And it's related to upstream activity of improper handling of these wastewater streams. Also, sending the same fluids to industrial treatment facilities. So these are facilities designed to handle and treat pretty nasty water streams, right? And they took out roughly 90% of the salts. So they're doing a much better job. However, they didn't get all the radium. And so when you looked at, this was a study by Warner et al., where they looked at the discharge of these oil and gas fluids from industrial treatment facilities, they found that radium was accumulating in the sediment downstream of the discharge. Right? This actually, after publishing this paper, shortly after publishing, I think about 500 feet of the river was dredged to remove the radium that was basically sorbed onto the clays in the river sediment. So these are just 2 examples of what not to do, right? But I would make the argument that Pennsylvania learned rather quickly. So this paper, and this is the last content slide that I have, shows how treatment or handling of these wastewater fluids in Pennsylvania evolved from 2008 to 2011. And as I said before, if the water that's collected isn't disposed in the subsurface, oftentimes it's reused to complete additional wells. And so that's what this black bar is showing you. That is water that's collected and then reused to frack another well. And that works really well as long as you're still drilling, right? So you take water from this to frack the next well, and it's sort of a game of hopscotch. Until at the end of the road, you're not fracking any more wells. Now you still have some water you got to deal with. But the bigger challenge is all those wells that you've completed are going to produce wastewater throughout the lifetime of those wells. And so you have a larger challenge than what is necessarily shown here, because this is still a very short time frame from when those are produced. But they basically, the state of Pennsylvania got rid of sending it to publicly owned treatment works, which would be sending it to a drinking wastewater, or a wastewater treatment plant, And industrial is this other bar, which actually doesn't show up very well on here. But this is injection disposal. So you're seeing the injection disposal is going down a little bit, which is coincident with reuse, but you're also producing a lot more water. I don't remember exactly, but each of those raindrops corresponds to some order of magnitude of wastewater volume. So I would say that it's an example of where regulators and industry operators learn pretty quickly and change their practices to improve the handling of this fluid. But the short story is that it's a real challenge, and it's something that we're still working on. And one of the challenges that we're looking at in my group is how do we deal with the radium? And so these are trace amounts of naturally occurring radioactive material that then get concentrated oftentimes in mineral precipitates during the handling or treatment process. And so then you go from very low level in water to effectively concentrating it in a smaller volume of mineral deposits. So in summary, I think I made a good case for convincing you that hydraulic fracturing in and of itself is not a new technology, right? But it is being applied at a much larger scale in combination with horizontal drilling, which has allowed us to go after unconventional resources at an unprecedented rate and success rate as well. There's obviously opportunities for improved best practices in well construction. So I said methane leakage, that was the big concern there was leakage up the casing, so improper well construction. So that's an opportunity for us to improve those practices. There's many open research questions. I think that's good from an academic standpoint, right? I'm very excited to work in this area. I think there's a lot of important work that is yet to be done, and there's a lot of people really rushing to the challenge. So I think we should feel good about that, at least being at the University of Michigan and in other universities and national labs. And I think that there's a lot of work that is advancing our knowledge at a much more rapid pace than it was 5 years ago. And I really believe that better communication among different stakeholder groups. And so this is the topic of hydraulic fracturing is such a polarizing issue, right? And I think the problem with it being so polarized is that you don't have good communication from either side. Everybody's talking their own language and they have an agenda. But realistically, if we're thinking about sustainable development, right? I pulled this out from Our Common Future. Sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs, right? That is the definition, and we're here to talk about sustainability. So I think that it's not going to be a binary solution, which is we will or we won't develop these resources. We probably are going to be developing our shale gas as we move forward. So we just need to make sure that we're doing it with all of these issues sort of in the back of our mind, and we're moving forward. And I like this as well, which is showing you sort of my Venn diagram of water, energy, and the environment, which is that we need to sort of find that balance because you can't have one in isolation of the other. And so we have to keep that in mind as we think about these sustainability challenges. Thank you all for your attention.
The type of lawn we use, which is usually fescue, ryegrass, and Kentucky bluegrass, not only is this grass not native to Michigan, it's not even native to this continent.